Welcome to Theory of Computation. This is lecture number 3. We have been reading chapter 3 from Sipser's book. I would like to encourage you to keep reading this chapter on your own, as it is very important for you to try to learn things on your own. I also hope that you have been doing the exercises that I have been assigning in these lectures, because without doing the exercises, there is no way you will be able to learn this stuff. So I must stress that after every lecture, try to review the material that we have covered, do the exercises, and try to read the relevant chapters and sections from the book. The overview of today's lecture is as follows. Today we will recall the definition of a Turing machine, which is, of course, the most important concept in this course. After that, we will define what a configuration of a Turing machine is. Then we would look at some examples, and then finally define what is the language accepted by a Turing machine. So let us recall that a Turing machine is specified by 7 things. Firstly, you have to tell me what are the states of the Turing machine. The second thing is you have to tell me what the input alphabet is. The third thing is you have to tell me what the work alphabet is. You have to tell me the start state. You have to tell me the accept state. You have to tell me the reject state, and the last most important component of a Turing machine is the transition function, which specifies how a Turing machine operates. So let us go and look at the example that we were working with in the last lecture. Once again, this Turing machine is a very simple Turing machine, and it only has 4 states. Q0 is the start state, QA is the accept state, QR is the reject state. The input alphabet is our favorite binary alphabet 01. The work alphabet consists of 0, 1 and the blank symbol. The transition function is given by the following table as shown below. Let us try to intuitively understand what this Turing machine does. Previously, we looked at this Turing machine in a rather mechanical way. Let us now try to see if the states have some meaning, and that would give us a more clear idea of what this Turing machine is trying to do. If we look at this Turing machine closely, the state Q0 has a meaning. It means that the machine has been scanning the input and the last symbol that it has seen was not a 1. So when the machine is in the state Q0, the last scanned symbol was either a 0 or a blank. That is the meaning of this state Q0. Similarly, the state Q1 has a meaning. When the machine is in the state Q1, that means the last symbol scanned by this Turing machine was a 1. So if we look at the transition table or the transition function very carefully, if the machine is in state Q0 and it reads a Q0, it stays in Q0 because the last symbol it scanned was a 0. On the other hand, if the machine is in Q0 and it scans a symbol which is a 1, it moves its head to the right but changes its state and goes to Q1, thereby signaling that the last input read was a 1. Similarly, when the machine is in the state Q1 and it reads a 1, it does not change its states and simply moves to the right. On the other hand, if it reads a 0, it goes back to the state Q0 and moves to the right. Therefore, these two states are remembering what was the last symbol that was scanned by the alphabet. Let us look at these two entries in the transition function. Well, the first entry says that if you're in state Q0 and you see a blank, then you should reject the input. And the second entry here says that if you're in the state Q1 and you see a blank, then you should accept the input. What does this mean? This means that the Turing machine will accept all inputs that end with a 1 and reject all inputs that end with a 0. This is the working of this Turing machine. The transition function can be given by a transition table, as you have seen before, but it can also be shown by a transition diagram. Let us look at the transition diagram of this Turing machine. The transition diagram of a Turing machine looks very much like the transition diagram of a DFA, which you're already familiar with. Let us have a close look at this transition diagram. The transition diagram here consists of 4 nodes. They're labeled Q0, Q1, QReject, and QAccept. Of course, these 4 nodes represent the 4 states of the Turing machine. Then if we look at this transition diagram, there are arrows going from some of the states to others. Let us look at Q0. There are 3 arrows coming out of it. This signifies the fact that we have specified what this Turing machine will do on all of the 3 possible symbols that are in the work alphabet. Well, the first arrow, which is labeled 0, followed by right arrow R, and it comes back to Q0, says that if the machine scans a 0, then it should stay in the state Q0 and move to the right. Similarly, the arrow that is labeled blank, right arrow R, says if the machine is in state Q0 and it sees a blank, it should move to the right and go to the reject state. Similarly, you can interpret all the other arrows. This diagram is a more clear picture of what the transition function is doing. So, how do we make a state diagram for a Turing machine? Well, there are very simple rules of making a state diagram. For each state in the Turing machine, you have to draw a node. And then you have to look at the transition function and draw arrows or edges going from states, which will be labeled as follows. Each state is represented by a node in the state diagram. Clearly mark the initial state, the accept state and the reject state. In this course, we will always mark the accept state with QA and the reject state with the label QR. For each state other than the accept and the reject state, there should be as many arrows coming out of the state as there are symbols in the work alphabet. Each arrow should be labeled by a replace symbol and a move. Sometimes, if the Turing machine is going to replace the symbol it's reading with the same symbol, so that means it is not going to change the tape contents, we will ignore specifying the replace symbol. So, for example, if an edge is labeled A, right arrow R, that means in that state, if the machine is going to read an A, it will simply replace an A by an A and move to the right. Since the correct way of writing it would be A, right arrow, A, R, which is more complicated, we just make a shortcut or by convention simply write A, arrow, R. That means if the machine is in a certain state, it reads the symbol A, it moves to the right. The arrows tell us what are the states, the new states that the Turing machine will go into. So state diagrams are a very convenient way for us to express what the transition function is. We are going to look at state diagrams of many Turing machines in this course. As a Turing machine computes, changes occur in it. There are 3 changes that occurs when a Turing machine takes a single step. The first change is its state can change possibly, its tape contents can change, and the position of its head can change and does change. So a setting of these 3 things is what we will call a configuration. A configuration of a given Turing machine tells you exactly about what's going on in the Turing machine. It tells you exactly what state the Turing machine is in, what are the tape contents, and currently which symbol is being scanned. So if someone tells you the configuration of a Turing machine, you should be able to take the Turing machine from that configuration and figure out what would be the next step that the Turing machine will take and what would be the next step and so on. However, we are not just interested in what the initial configuration of a Turing machine is going to be. We are interested in taking a snapshot of a Turing machine during the course of its computation. So a configuration is what you should think of as somebody taking a snapshot of the Turing machine while it's performing its computation. We will be representing a configuration in a very special way. Suppose gamma is the tape alphabet, and let's say U, V are two strings in gamma star, and Q is the state of the Turing machine. Then the configuration U, Q, V denotes the following. It denotes that the current state of the Turing machine is Q. The tape contents are U followed by V, or U concatenated with V, and the tape head is reading the first symbol of V. It is assumed that the contents are all blanks after the last symbol of V. Let us look at the following picture. This picture shows a Turing machine which is in the middle of its computation. The machine is in the state Q7 and the tape contents are 101, 101, 111. And the tape head is currently reading the fifth symbol, which is a 0. What I have described to you is a configuration of this Turing machine. I have described to you what state this Turing machine is in, what are its tape contents, and which cell is being read by the tape head. Similarly, the picture that I showed you was visually giving the information to you. I had shown the tape contents, where the head was pointing, and of course, the state was also mentioned in the diagram. So, this is what a configuration is. Now, the question is, how will we denote this configuration using our notation? Well, let's think about it a little bit. The first thing we will do is find out what are the contents of the tape which are being read before the cell that is being read by the head. Okay, so we will take all the tape contents before the cell which is being scanned by the tape head. That would be our U. After that, we will write down the state of this Turing machine, which happens to be Q7. After writing down the state, we will write down all the remaining symbols that are there on the tape. Let us see what the configuration in our notation will be for this example. In this example, the first 4 symbols constitute of U, and the last 5 symbols constitute of V. The state is Q7. So this configuration will be written as 1011 Q7 0 1111. See, by looking at this configuration, I can tell exactly where the tape head is, what it's reading, and what are all the contents of this tape. So in this short form notation, I can convey a lot of information, namely what the snapshot of the Turing machine is. Well, let's try to go the other way now. Suppose that I tell you that a machine is in a configuration 0A, BBA, Q3, BBA01. Can you draw a picture of this Turing machine and show me what is the configuration this Turing machine is in? Well, the tape contents are easily recovered from in this notation by ignoring the state in the configuration. So if I were to drop Q3, then I realize that what is on the tape is 0A, BBA, BBA01. And of course, the machine is in state Q3. That's also clear by looking at the configuration. Since I see only one state there, the machine must be in that state. Last and most important thing is, which symbol is the machine currently reading? Well, the machine is currently reading the 6th symbol. That's because Q3 is the 5th symbol on the tape. So the Turing machine is reading the 6th symbol, which happens to be a B. Let us look at the picture of this Turing machine in this configuration. As you can see in this picture, the machine is shown to be in the state Q3, and the tape contents are 0A, BBA, BBA01, and the machine is reading a B, which is residing on the 6th cell of the tape. Let us look at one more example. Suppose that I tell you that a Turing machine is in the configuration 0, 1, Q2. What does that mean? Well, in this case, I have told you what U is, I have told you what the state of the Turing machine is, but what is V? Well, you're right. V is the empty symbol. What does this configuration mean in terms of drawing a picture? Well, this means that the machine tape contents are 0, 1 followed by all blanks. and the machine is in state Q2 and it's reading the third tape cell which happens to contain a blank. Here is a picture of the configuration. What you should be able to do is, if I give you a configuration in this notation, you should be able to quickly draw a picture, and if I give you a picture, you should be able to quickly write that configuration in the notation that we have just learned. I would like you to practice this, and there are certain exercises that are given in this lecture handout which you should do before coming for the next lecture. Now what we would like to do is formalize what does it mean for a Turing machine to take one step. This is done in terms of configuration. Let's say that a Turing machine is in a configuration C1. We say that a configuration C1 yields another configuration C2 if the machine can move legally from C1 to C2 in a single step. Let us be a little more mathematical and formal with this definition. Suppose that A and B are two alphabets in the work alphabet, and U and V are two strings over the work alphabet, and let us say that QI and QJ are two states of the machine. We will say that U, A, QI, B, V yields U, QJ, A, C, V if delta of QI, B equals QJ, C, L. What does this really mean? This means that if the Turing machine is in a particular state and it's reading a symbol B in the state QI, and the transition function asks the Turing machine to replace that symbol by a C and move left, then the next configuration of this Turing machine will be given by U, QJ, A, C, V. As you can see, in the next configuration, the machine has moved from state QI to QJ. It has replaced the symbol B and moved to the left. Here is a picture of what the yields relation does in this case. This only handles the case when the Turing machine is moving to the left. What about when the Turing machine is moving to the right? Let's have a look at that. Let us say that the Turing machine is in the state UA, QI, B, V, and delta of QI, B is equal to QJ, C, R. This means the delta function is saying that if the machine is in state QI and reading the symbol B, it should move into the state QJ, replace the symbol by a C, and move to the right. In this case, U, A, QI, B, V will yield U, A, C, QJ, B. As you can see, the machine has moved one step to the right and replaced the cell which contained a B with a C. Let us see a picture of what is going on here. We have not completely specified the yield relation yet. For example, we have not specified what happens when the tape head happens to be at one of the ends of the configuration. Let us do that now. In the special cases when the head is at the end of the configuration, the yields relation is defined as follows. Let's look at the case when the head is at the left end. Suppose the Turing machine is in configuration QI, B, V. As you can see, in this case, U is equal to the empty string, which means the machine is scanning the leftmost symbol. Now suppose that delta of QI, B is equal to QJ, C, L. So the delta function says that if the machine is in state QI and reads the symbol B, it should go into the state QJ, replace the symbol C, and more importantly, move to the left. In this case, there is no cell to the left of the first cell to move to. So we would say that this configuration QI, B, V will yield QJ, C, V. This is like saying that the machine is not allowed to move its head further to the left than the leftmost cell. This is just a convention, and we will follow it. Let us look at another case. Suppose the machine is in configuration QI, B, V, and delta of qi comma b is equal to qj comma c comma r. In this case, the machine is reading the leftmost symbol, which happens to be a b, and the delta function says that the machine should go into the state qj, replace the symbol with a c, and move to the right. Of course, in this case, there's no problem. We would say that qi bv yields c qj v. That means the machine will replace the symbol b with a c and move to the right. Of course, in this case, we have agreed that once the machine is scanning the leftmost cell and the delta function requires that it moves to the left, it would not move to the left but stay on the leftmost cell. There are some other cases to be discussed. For example, what if v happens to be the empty string? What if the head is reading a blank? Suppose the Turing machine is in the configuration UAQI. This means the machine is reading a blank symbol. Now we will consult the delta function and see what delta of qi comma blank is. If it is qj comma c comma l, in this case UAQI would yield u qj a c. The machine has simply replaced the blank symbol with a c and moved to the left. Similarly, if delta of qi comma blank is equal to qj comma c comma r, in this case uaqi would yield uacqj. Once again, the machine has replaced the symbol blank with a c and moved to the right, and therefore is now reading another blank. Have we discussed all the possibilities? Have we completely specified the yields relation? Actually, one annoying detail is left. What if the Turing machine is in the state qi? What does that mean? That means the machine is in the state qi and the tape contents are completely blank and the machine is reading the first symbol. The first symbol which happens to be a blank on the tape. So the head is on the leftmost cell. We have not specified the yields relation in that case. Let us do that now. Suppose the machine is in the configuration qi and delta of qi comma blank is equal to qj comma c comma left. In this case, the machine is supposed to replace the blank with the c and move to the left. But as we have agreed, if the machine is already on the leftmost symbol, the head will stay at the leftmost symbol. So qi in this case will yield qj comma c. On the other hand, if delta of qi comma blank is qj comma c comma r, then the machine can actually move to the right. So qi would yield c qj. This completely specifies the yields relation. Let us look at the summary once again. Let's see what the yields relation is telling us. The yields relation is telling us how the Turing machine takes a single step. The most important part of this relation is when it tells us what the machine does in a single step when the symbol that is being scanned is in the middle of the configuration. In this case, you have to remember that UAQI-BV yields UQJ-ACV if delta of QI comma B equals QJ comma C comma L, and UAQI-BV yields UACQJV if delta of QI comma B equals QJ comma C comma R. It seems that the yields relationship is very difficult to remember, but if you think about it intuitively, it's not very hard. All it is telling you how the machine takes one step. If the delta function is telling the machine to go into a state QJ and move to the left, replace the symbol C, then the new configuration will just reflect those changes. You will simply move the tape head to the left, replace the current symbol with a C, and move into the new state QJ. So the yields relationship is not hard to remember if one thinks about it intuitively. Let us look at the previous example of the Turing machine. We looked at its state diagram. The machine consisted of only 4 states, and let's see how this Turing machine operates using the help of this new notion of configurations that we have just learned. Well, let us say that we run this Turing machine on the input 1001. The Turing machine will initially be in the configuration Q0 1001. This means the machine is going to be in its start state and the tape contents are going to be 1001 followed by blanks. Now, if we apply the yields operation repeatedly, what do we get? Well, let's see. Delta of Q0, 1 is Q1, 1 R, which means the machine is going to move right, and it's not going to change the symbol 1, but it's going to change its state to Q1. So the new configuration is going to be 1, Q1, 0, 0, 1. After that, the machine is in state Q1, so we go and look at the delta function and see what is delta of Q1, 0. Well, that tells us that we should move into state Q0, don't change the symbol, and move to the right. So the next configuration is 10 Q0 0 1, and the next configuration, as you can see, is 100 Q0 1. That's because delta of Q0, 0 is once again saying that we should stay in the state Q0, don't replace the symbol, and move to the right. After that, the machine again goes into state Q1 and moves right, and so the second last configuration shown here is 1001 Q1. After that, the machine is in state Q1, and now we have to consult delta of Q1, blank. In this case, we realize that delta of Q1, blank is QA, so the machine will go into accept state. It will replace the blank with the blank and move right. So the final configuration of this machine is going to be 1001 blank QA. If a Turing machine is in a configuration C1 and the configuration C1 yields the configuration C2, we usually denote this by the following notation. As you can see, here we have C1 followed by this symbol, which we will call the yield symbol, and it would be read as yield, and then a C2. The subscript M denotes here the machine. Okay, if the machine is sometimes clear from the context, we will simply drop this subscript from this symbol yields. There are 3 very important configurations or kinds of configurations that we must be familiar with. First of all, a configuration that we are going to call the starting configuration. Suppose you give input W to a Turing machine M. In this case, the starting configuration would be Q0W. So Q0W is the starting configuration of a Turing machine on input W. Remember that the starting configuration is not a single configuration of the Turing machines, but depends on the input. For each different input W, we have a different starting configuration, and this configuration is specified by writing Q0 followed by W. It simply says that the Turing machine has its head on the leftmost cell, and the tape contents are exactly W followed by all blanks. So the starting configuration is the configuration in which the machine starts in. We give it an input, it's in the start state, and the tape contains the input only followed by all blanks. Another kind of configuration that is very important is called the accepting configuration. Well, in an accepting configuration, the machine reaches accept state. So any configuration of the form U, QA, V is called accepting configuration. Another configuration that is going to be very important is called the rejecting configuration. These are all configurations in which the machine has reached a reject state. They have the form U, QR, V. These 3 kind of configurations are extremely important. The starting configuration is when the computation of the Turing machine starts, and the accepting and the rejecting configurations are when the computation of the Turing machine ends. All other configurations are intermediary. This means the machine has not finished its computation, but it's in the process of computing. The accepting configurations and the rejecting configurations are also called halting configurations. Halting means that the machine has stopped performing its computation. So the accepting configurations and the rejecting configurations together are called halting configurations. Let us now define what is the language accepted by a Turing machine. Suppose M is a given Turing machine and W is an input over the input alphabet. So W is an element of sigma star, not gamma star. Gamma is the work alphabet. The input alphabet is sigma. So we take a string W over the input alphabet. We say that a Turing machine M accepts W if there exists configurations C1, C2 up to CK such that the following three conditions hold. C1 should be the start configuration of this machine M on W. That is, C1 has to be equal to Q0, W, where Q0 is the start state. The other thing is that each Ci should yield Ci plus 1. What does this mean? This means from the first configuration C1, the Turing machine should be able to go into C2 in one step. From the second configuration C2, the Turing machine should be able to go into C3 in another step, and so on and so forth, and eventually reach CK, which is an accepting configuration. So if all these three conditions hold, we will say the Turing machine M accepts a string W. Intuitively, what it means is what we would like it to mean. If we take the string W and give it to the machine as an input and turn it on, after doing certain amount of computational steps, it should eventually reach the accept state. In this case, we will say that the input is accepted by the Turing machine. Now, what is a language accepted by a Turing machine? The collection of all strings in sigma star that are accepted by the machine is the language accepted by M and would be denoted by L of M. So L of M mathematically is the set of all W in sigma star such that M accepts W. Let us look at the example that we have been working with. Let us look at our previous Turing machine, which consisted of 4 states given by this diagram. We have analyzed this Turing machine quite closely. What is the language accepted by this particular Turing machine? Well, as we noticed, this Turing machine is going to accept all strings that end with a 0. So L of M in this case is the set of all strings over the alphabet 0, 1 over the binary alphabet which end with a 0. As we saw, our example Turing machine accepts all strings that end with a 0. So the language of this Turing machine is the set of all strings which end with a 0. On the other hand, if we give it an input that does not end with a 0, the machine rejects this input. So all strings that do not end with a 0 are not in the language. So the language is completely specified by saying that it's the set of all strings that end with a 0. But the question now is, does a Turing machine always accept or reject strings? Let us look at another example. Here I have made a Turing machine M prime by slightly modifying our previous example. What I have done is I have changed the delta function so that delta of Q0, comma blank is equal to Q0, comma blank, comma R. What does this mean? This means that if the machine is in state Q0 and it reads a blank, it continues to move to the right and replaces the blank with a blank. So as long as the machine is reading a blank, it will continue to move to the right. Let us first look at the state diagram of this Turing machine. As you can see, it almost looks like the same diagram as before, except for one simple change. Let us see what this Turing machine will do if I were to simply give it the input 0. The machine will be in the state Q0, it will read a 0 and move to the right. Then it will read a blank and replace the blank with a blank and move to the right again. Then it would read another blank, replace the blank with a blank and move to the right. And all this time the machine will remain in the state Q0. It will continue to read blanks and continue to move right forever. So this machine will keep on computing forever. What is the language accepted by this Turing machine M prime? Does it even make sense to talk about the language accepted by this machine M prime? Well, for that, we will have to go back to the definition. The definition of the language accepted by a machine M was the set of all strings that the machine accepts. So in this case, the machine M prime accepts exactly the same strings as the machine M before. So the language accepted by this Turing machine is the set of all strings that end with a 0. In this case, however, if a string is not in the language, the machine does not reject them. It simply computes forever. However, according to our definition, L of M prime is the set of all strings that are accepted by this Turing machine. So if we collect the set of all strings that are accepted by this Turing machine, we get exactly the same set as before, namely the set of all strings that end with a 0. So M and M prime accept the same languages. It turns out that we prefer the first machine over the second machine M prime, because the first machine gives us a definitive answer on all inputs, whereas the second machine only accepts the strings that are in the language. In this case, M is called a decider. Let us be more formal about this definition. A Turing machine is called a decider if it halts on all inputs in sigma star. So if a Turing machine halts on all inputs, it gives us a definitive answer, reject or accept on all possible inputs. We call it a decider. Let us now come to one of the most important problems in computer science. Usually, a very important problem in computer science is that you're given a language, which is actually a problem, and you're asked to design a decider which accepts that language. That means you are asked to design an algorithm for solving that problem. So a typical problem in computer science looks as follows. You're given a language L0 and you're asked to decide a decider M such that L of M is equal to L0. L0 is the given problem and M is the algorithm that solves or decides the problem. Let us look at an example of this. Let us take sigma to consist of only one symbol 0, and let us say that L2 is the set of all strings 0 to the 2 to the n such that n is greater than or equal to 0. We want to design a Turing machine M2 such that L of M2 is equal to L2. Hence, we want to design a Turing machine M2 that accepts all the inputs in L2 and rejects all the inputs that are not in L2. So we want M2 to be a decider. In order to solve this problem, first we will have to understand the language L2. What does this language L2 consist of? Well, we can take various values of n and see what are the strings that this language consists of. It consists of the string which is a single 0, 2 zeros, 4 zeros, 8 zeros, 16 zeros, and so on. So if the number of zeros in the string is a power of 2, then the string belongs to this language. And if the number of zeros in a string is not a power of 2, then the string does not belong to this language. Our goal is to design a Turing machine that accepts this language. That means our goal is to design a Turing machine which will accept all strings in which the number of zeros is a power of 2. So the machine should accept a single 0, 2 zeros, 4 zeros, 8 zeros, and so on, and it should reject if I give it the empty string, or if I give it 3 zeros, or if I give it 17 zeros, or any zeros, any number of zeros that is not a power of 2. How would we design a Turing machine? Well, For this, we need to have some intuitive idea. To design a Turing machine, we must have a plan in mind. How will we solve this problem? Note that a Turing machine can have only finite number of states, and therefore it cannot remember much. It does not even know how to count, unless you teach it to. Well, here is a very interesting idea. If I have some number of zeros and I cross out each alternate one, I cut the number of zeros into half. Of course, if the number of zeros is odd, then I will not find the alternate zero in the end and discover that the number of zeros in the string was an odd number. So let us first describe this Turing machine M2 informally. The idea is this Turing machine will sweep from the left to the right through its input, and it will try to cross off every other zero that it encounters. Now, if there is a single zero on the tape, the Turing machine will accept. If there were more than one zeros and the number of zeros was odd, then the Turing machine will reject. And otherwise, the Turing machine will return its head to the leftmost end and repeat this process. Let us think about what would happen if we were able to successfully design this Turing machine. This Turing machine, let's say if it gets 20 zeros, will cross off, in the first phase, it will cross off every other zero, and so it will be left with 10 zeros. Then it will cross off every other zero in the second phase, and it will be left with 5 zeros, and then it will try to cross off every other zero and discover that the number of zeros on its tape left was an odd number, and therefore it will reject this input. On the other hand, if the number of zeros on the tape were 8, once it crosses off every other zero, the number of zeros left would be 4, which would be reduced to 2 in the next phase, which would eventually be reduced to 1, and then the machine will accept this input. So this seems like a reasonable plan. Let us look at the details of this Turing machine. The formal description of this Turing machine is as follows. Once again, always remember, when you have to specify a Turing machine, you must specify 7 things. This machine M2 is equal to Q, sigma, gamma, delta, Q1, QA, QR, where Q, the set of states, is given by Q1, Q2, Q3, Q4, Q5, QA, and QR. The input alphabet sigma consists of a single symbol 0. The work alphabet will consist of 3 symbols 0, X, and blank. Q1 is going to be the start state of this Turing machine. QA is going to be the accept state. QR is going to be the reject state. The delta is described by the following state diagram. The state diagram of this Turing machine looks pretty complicated, as it consists of a lot of states. But if we look at various parts of this state diagram, we would be able to tell what this Turing machine is doing. Q1 is simply the start state, and if in the start state the machine sees a blank, it simply rejects the input. So Q1 just makes sure that there is at least 1 0 present in the input. If Q1 sees a 0, it will change it into a blank and move R. The advantage of doing that is now the first symbol has been turned into blank, so when the head is scanning towards the left, when it sees a blank symbol, it will know that it has reached the leftmost cell of the tape. In the state Q2, if the machine sees a 0, it crosses it off because the machine is supposed to cross off every alternate 0. Another 0, it crossed it off. Then it goes into the state Q3. Q3 and Q4 are where the bulk of the work is done by this Turing machine. As you can see in the state Q3, if the machine reads a cross, it simply moves to the right. If it sees a 0, it does not change the 0, but only moves to the right and goes into the state Q4. This means the machine has seen 1 0 and is now waiting for another 0 in order to cross it off. If you look at Q4, if the machine sees a cross, it does not do anything and moves to the right. But if it sees a 0, it crosses off that 0 and moves to the right and goes back into the state Q3, thereby crossing off the alternate 0 and going back to Q3, which will once again wait for another 0 before going into Q4. So the machine, when it's alternating between the state Q3 and Q4, once it skips a 0 and the second time it crosses off a 0. This will continue to happen, and if the machine is in state Q4, then it has seen an odd number of zeros, and if the input ends, the machine simply rejects the input. On the other hand, if it's in state Q3, then it has seen an even number of zeros, and now if the machine sees a blank, it starts moving to the left. The state Q5 is going to move the head all the way to the left till the machine sees the blank. Remember, we had put a blank in the first cell, so we are guaranteed to find it. So the state Q5 replaces zeros with zeros and moves to the left, and replaces a cross with a cross and moves to the left till it finds the first blank, and then moves to the state Q2, where this process is repeated again. Of course, if in the state Q2 we see a blank, we go to the accept state. So this state diagram implements the plan that we had outlined informally. Let us look at a sample run of this Turing machine on the input 000. As we are now familiar with configuration, we'll start with the starting configuration and see, using the yields relation, what are the various configurations that we get as this Turing machine computes. This is shown in the table. As you can see in the workings of this Turing machine, it tries to cross off every alternate 0 and makes sure that in the end there is only one 0 left. If it succeeds, it accepts the input. Today we have looked at many examples of Turing machines. We have defined what configurations are, we have looked at the yields relation, and we have defined what a language accepted by a Turing machine is. We have also defined when a Turing machine is a decider and when it is not a decider. A Turing machine is a decider when it halts on all inputs, when it gives us a definite answer on all possible inputs. In the next lecture, we will continue with these concepts. I hope to see you next time. Thank you and goodbye.